about, so first of all, as some of the other guest lectures are hard because you're one-off in the middle of a course. I went back and looked at the videos of the stress strain lectures because I'm going to sort of build on that. But I also I feel like I have the opportunity to talk about some little different things and some things that are related to stress and strain and mechanical behavior of materials. It also integrates a little of the concepts that Professor Kirby talked about in his lecture that I'll get to in a little bit. And like I said, guest lectures are always hard, so please ask questions. And my goal is to give you some application, really, of stress and strain. So what do I mean by that? I mean that my work is all related to this topic of mechanics of biological materials. You've done a lab where you've done some bending of some different materials, if I'm not mistaken. What were the materials you guys tested in lab? Steel, PVC, and what was the other? Brass, okay. And what did you find there? What was different from going from steel to brass to PVC? Young's modulus. Anybody else find Young's modulus? And if we were to rank, so you did brass, PVC, steel. How do those? What was the maximum Young's modulus? Steel. What was the minimum Young's modulus? PVC. And so brass fell in between. Can you give me some idea of what your numbers were? Anybody remember? Steel, any idea? What were the units that we're looking at?
Pascals.
Pascals?
Or gigapascals, either one.
Some unit of pascals. Maybe gigapascals is what's suggested here. Anybody else remember having gigapascals? Okay, so we have some value in gigapascals. Anybody give me some ballpark number that you had there? 70? 30? 200? I think you guys made these measurements yourself, right? You put some weights on, you plotted some numbers and got a modulus from that? Nobody remembers any of the numbers? Well, let's pick a round number, and I'm going to suggest that maybe a number of 200 is a good number, and we heard 200 up here, but I heard a bunch of different numbers. What about PVC? 30?
Yeah.
You don't remember if it was half, a tenth, 2 orders of magnitude? Anybody remember the numbers you had in that lab?
Like a 1.
I actually don't know. I've never tested PVC, so I'm interested in what it is because actually it's relevant to what I'm going to talk about, which is why I was coming to you all, as the experts, having tested PVC for what the properties are. 100 times less, so let's say 2 gigapascal maybe? Okay. 2 gigapascal. Okay, so I want you to think about those numbers. So what do you have here? You have a metal that's pretty stiff in terms of its modulus, and then PVC is a plastic. Were the geometries of the 2 specimens the same? Yes. Yep. And your equation took that into account regardless, right? So you have a metal you tested and a plastic. And we have 2 orders of magnitude of values here. Well, so I want to talk about some biological materials. And let's keep this scale in mind as we talk about that, okay? So why do we care about the stiffness of materials? Why would we care what the modulus is? Well, you design things and you need material properties because we're designing for particular behaviors and particular load-bearing capacity. Well, and so what my research looks at is a slightly different twist on this, and so I don't look at steel and PVC, although I'm very interested in their properties. And why I'm interested in their properties? Well, I look at different materials. I look at the skeleton. And so this is a picture of a human skeleton. We want half, sort of. Well, this is actually still fairly bright. So this is what I work on. This is the skeleton. It's made up of a variety of different tissues. What tissues are in your skeleton? in the body? Anybody know?
Bone marrow?
Bone marrow. Anything else?
Cartilage.
Cartilage. Connective tissue. I heard ligament. Anything else? Muscle. Blood. Yes, lots of blood. It's a whole bunch of tissues. Now, what I want to talk about is where in your spectrum here of mechanical behavior these tissues fall. But I want to put a little context to this first. And so if you were to guess, let's say bone, okay? And so first of all, why would a mechanical engineer, so I'm a mechanical engineer, all my degrees are mechanical engineering, why would a mechanical engineer be interested in bone? Or what's relevant in bone to mechanical engineering and vice versa? Replacements, okay, yep. Anything else? So I put a question up here. What do you think the functions of the skeleton are? What does the skeleton do in the body? Supports it, yep. Anything else? Provides structure, yep.
Protection.
Protection, what does it protect?
Your rib cage protects all your lungs and heart.
Yep. So if I pound myself on the chest, I'm not hitting my heart, my lungs, all sorts of organs are back there that are protected, and that's actually really important if you think about what we do on a daily basis. That, you know, putting your backpack on, you don't want to hit your heart, right? So protection is actually, and again, it's a very mechanical function. Going back to support, it's a slightly different mechanical function. Anything else that you think the skeleton does? Movement, with the muscles, yep. So I've heard lots actually of mechanical things now. So this is why I'm a mechanical engineer. Now this is a biological structure. Do you think it does anything else biologically? I can't hear.
Blood cells.
Blood cells, yep, actually. So it turns out your red blood cells are made in the marrow in your skeleton. That's really important. Anything else?
Spinal cord is connected to the brain. So like
Spinal cord's connected to the brain, so that goes back to sort of a protective function, and I'd say. So in the spine, the skeleton protects the spinal cord. Is that what you're trying to say, or you mean something else?
No, I'm linking with the nervous system.
Linking to the nervous system, okay.
What
Yep.
about hearing?
Hearing?
Bones in the ear.
There's bones in the ear, yep. Any other functions?
Growth.
Growth, yep.
Balance. Big toes.
Yep, balance, okay. That's sort of the whole organ as a unit is doing a lot of these things. Anything else? I guess one more sort of broad function, and that hasn't come up, is anybody drink milk? Anybody watch the Got Milk ads? Yeah, sorry, I don't have the clickers today, so no clickers because of I don't have the technology installed on my laptop, so we have to just raise hands. So anybody drink milk? What's in milk? Well, so lots of people drink milk. Why do you drink milk?
Calcium.
Calcium. Where's the calcium go?
Bones and teeth.
Bones and teeth. What else is calcium good for? Why do it goes to your bones and teeth, but why is that all you need it for? Or does it do anything else in the body? Does anybody know?
Nervous system.
Nervous system, yep. Every single time a neuron fires, it's calcium that's firing and helping you actually to the neuron to function. Anything else? Some of you must have some biology. It turns out calcium is important for almost every function in the body. So your muscles don't contract. Your calcium is key to your muscles contracting. Calcium is key to cell signaling for anything, any type of cellular function. Calcium is often the second messenger. So calcium is really important. So, and 99.9% of your calcium is stored in your skeleton. And it gets put in and out, gets taken in and out there, but it's a big reservoir of calcium. So this is the list of sort of generic skeletal functions that I put together. And so everybody mentioned structural support, protection of vital structures. This calcium reservoir is what I'm referring to as mineral homeostasis. And then the making of red blood cells is really a critical function of the skeleton. I should add that besides calcium, a lot of other minerals are also stored. So all your phosphorus is stored in your skeleton as well. So it has it's a huge mineral reservoir. And yes, the minerals function in bone, but they also function in the body. And if you don't have enough calcium in your diet, for example, you take it out of your skeleton. So there's an interplay here between the biological function and the mechanical function. Okay? So then going back to why does a mechanical engineer study this? Well, let me show you a little information. So I'm interested in osteoporosis. Anybody know what osteoporosis is? Sorry, I can't quite hear you.
Your bones degenerate and you lose strength.
Your bones degenerate and you lose strength. There's a lot of information in that statement. Anybody else have any other ideas of osteoporosis? That's what you all would have said?
Is it related to arthritis at all?
Is it related to arthritis? Maybe. So arthritis is more of joints and cartilage. And in general, it used to be the paradigm that people that got osteoporosis tended not to get arthritis. But there's actually some suggestion that there is an interplay, actually. So yeah, but arthritis is a little bit more cartilage, but it also affects the bone. But it's different than osteoporosis. Anything else that you've heard about osteoporosis?
Well, is it like calcium deficiency? Because like when they, over 50, like take much more calcium.
So calcium deficiency, and when you go over age 50, what happens at age 50? Why age 50? Anybody have any ideas of what happens at age 50? A magic number? Okay, so anyway, so osteoporosis is a disease whereby the skeleton changes, and it changes in multiple ways, and we're going to talk a little bit about what some of the things are. I guess I'm not going to talk so much about osteoporosis per se, but what the contributing factors are to the skeletal mechanical behavior. But what the worst outcome of osteoporosis is, it's not losing bone, but it's if you break bones. And if you break bones, actually, if you are osteoporotic and if you break your hip, and you are, and actually, and particularly in males and men, and it's less common in men than in women, but you actually, in the year after you break your hip, your chance of dying is way increased. So there's a huge mortality associated with breaking your hip. And so you'd like to keep people from breaking their hips because it increases their risk of dying, to put it very simply, sort of. But there's also lots of function. So if you break your hip, there's lots of other things you can't do. So there's this increased risk of mortality, but there's lots of associated other morbidities and other problems. So what the main problem outcome is if you break something. And there's 3 sites at which you tend to break things if you suffer an osteoporotic fracture. You break your wrist, and most wrist fractures are associated with falling, because if you fall, the first thing you do is you stick your arm out. And that's associated then with a fracture that happens in the first third of your wrist. Second type of fracture, working our way in, is in the spine. And these are often asymptomatic. You don't even know you have them, but you notice you're getting shorter maybe, or you notice you have some back pain. And then you go to an x-ray and you discover there's a fracture there. And then the third type is the hip fractures. About half of them occur in the spine, and then the other half are distributed between the hip and the wrist, and some other sites as well. So to show you what when these fractures looks like, here's an example, and I apologize, these x-rays are a little hard to see. This is an x-ray of the spine, so this is the spinal column running right here, and what you can see here is a nice square intact vertebra. Here's another vertebra that's intact, and here we see one that has a fracture. You see how the height of this vertebra here is about half the height of these other two, and so it's compressed. It looks like a wedge fracture is what's called because it's now wedge shaped. But this used to be a nice cuboid-shaped vertebra, and here it's no longer that shape because it's fractured. So this is an example of a spine fracture. And then this is an example of a hip fracture. I've got 2 different images. This is actually a hip fracture that's going down the shaft of the hip, sort of, more. And then here's a hip fracture that's right here, that's in what's called the neck of your femur. So this is your hip joint right here. Here there's the shaft coming down, and here's a fracture sitting right there. So again, why would a mechanical engineer have anything to contribute to hip fracture or spinal fracture? Why would I be interested in doing that in my research area now? Engineering of hip replacements, okay. Let's step back before we even get to the replacement. What about the fracture?
How to repair it.
How to repair it?
Stresses that cause it.
Stresses that cause it. So step before repair is what causes this fracture. So you've been talking about how you look at stress and strain and what stress and strain are, but the exact same thing applies to these skeletal structures. So I'm going to go off the slides in a second, but I just want to suggest that fracture by itself is a purely mechanical event. So there's more load applied to the structure. The structure here is your spine or your hip than it can take, and so then it fails. And so it doesn't matter biologically really what's going on. This only happens with loading, and somehow the load that was applied exceeded the load capacity of either the spine or of the hip. So thinking about this very simplistically, whoops, sorry, I didn't realize this was animated. This is another different image of another spine fracture where you can see this is a different type now. It's totally hourglass shaped and this thing is just compressed. But what we have when we think of the mechanics of fracture is we have some forces that are applied through the activities that you're doing.